Hello, and in this video I will be solving this problem 4.16 block and wedge from David Moran's Problems and Solutions in Introductory Mechanics. In this problem we are presented with a block and a wedge, unsurprisingly, which are sitting on a frictionless table. All the surfaces here are frictionless except this block is pressed up against a wall, which constrains its motion to move purely in the vertical direction. And we are tasked with finding the subsequent acceleration of this lower wedge right here as when we let go of this block and let it slide down. So the first thing I'm going to do is draw a free body diagram for both blocks. So for the large block right here, it will feel its weight, mg, pointing downwards, and it will feel a normal force from the wall, so let's call that NW. And lastly, it will feel a normal force from the plane below, NP. As for the little block right here, this will feel, first of all, an equal and opposite reaction force from the block that's sitting on top. It will feel its own weight, little mg, and it will feel a normal force from the ground. And let's label these angles. So we know that the angle of the inclination of this wedge is theta. So the angle of inclination right here, or this angle, will be theta as well. And now these free body diagrams should be complete. So let's now proceed to making equations to describe the motion that we will see in these diagrams. So first of all, we know that NW is equal to NP sine of theta. This is because this block cannot move in the left or right direction, so these forces must be balanced. There's zero acceleration. The second equation that we can write is that the normal force from the ground on the plane is equal to mg plus np cosine of theta. And this is because there's no acceleration of this plane going up or down, so these forces must balance. We want to find the acceleration of the plane in the x direction, and you can see that the only force acting in the x direction on the plane is going to be np, so you can say that the acceleration of little m in the x direction will be equal to np sine of theta. Let's look at this larger block right here, and you can see that np right here, np, or rather, I wrote that wrong. You can see that large M, I'm saying to y, so the acceleration in the y direction of this larger block, big M, is equal to mg minus np cosine of theta. Now the signs on here are kind of weird, so let me just make sure. So the acceleration in y will be in the same direction as gravity and opposite to the normal force for going upwards. So this should be correct. However, we still need one more equation to describe the connection between the x acceleration and the y acceleration. And in order to do that, we have to take a closer look at the diagram that we were given. So you can see that this large block is sitting on a plane, and if we were to push this large block down a certain amount y, you can see that the plane would have to move accordingly a certain amount x, and this amount is actually described by tangent of theta is equal to y over x. So this is our position constraint, and I'm just going to stretch this out a little. X tangent of theta. x tangent of theta. And now I'm just going to take the double time derivative of these, which will just mean I find the acceleration. So ay is equal to ax times the tangent of theta. I'll rewrite that over here. Ay is equal to ax times the tangent of theta. So that is our last equation that we need to describe all of the motion of this system. Just erase this so we have some more room. Alright. So the first equation I'm going to take is going to be this one right here. I'm going to rewrite it right here. MAX is equal to NP sine of theta. And then the second equation I'm going to take from what we wrote down is actually this one. So this one, I'm just going to rewrite it. It's equal to mg minus np cosine of theta. I'm going to move this mg to the other side. May minus mg is equal to minus np cosine of theta, and therefore mg minus may is equal to np cosine of theta. And then I'm just going to move this part up here, rewrite it for clarity. To show you this trick that I'm about to do, which should make things pretty easy to solve here. And as you might be able to tell now, I'm going to divide these two equations in order to eliminate the NP, which is causing some problems right now. So little m ax divided by mg minus may is equal to tangent of theta. Alright, so max is equal to mg tangent of theta minus m, and then ay tangent of theta. Max is equal to mg tangent of theta minus max tangent squared of theta. All I did was plug in this equation right here. Now I'm going to move ax to the same side, so it's going to take this and move it up here. So I'm moving all the ax's to one side, so ax plus big M ax tangent squared of theta is equal to mg tangent of theta. All I did was add it to both sides. Factoring out ax, you get m tangent squared of theta plus little m is equal to big mg tangent of theta. Ax is equal to mg tangent of theta divided by m tangent squared of theta plus little m. And this is our answer, actually. The horizontal acceleration of the wedge. Now, the textbook actually gives it in a different format. The textbook shows as ax is equal to mg sine theta cosine theta divided by m sine squared of theta plus little m cosine squared of theta. And through some trigonometry, you can show that these two are actually identical. But anyways, this is our final answer. And that is how you solve this problem block and wedge 4.16. Thank you.